All right, let's do number 12. 4-point charges are at the corners of a square as shown at the right. If Q equals 0.10 microcoulombs and A equals 5 centimeters, A, what is the net force on the plus 2Q charge? B, what is the E field at the location of the plus 2Q charge if the plus 2Q charge is removed from its position? And finally, C, what is the E field at the center of the square? Okay, so you start this problem with your diagram. I just copied it out of the workbook. And so you know that these distances are 0.05 meters as given by the problem, and that the charge of Q is going to be 0.10 times 10 to the negative 6 coulombs, as 1 microcoulomb is times 10 to the negative 6. And so they want you to find the net force on this charge here. So you just look at all the other charges and you see, you know, what kind of forces they apply onto this guy. So if you look at this charge, this plus Q charge is repelling this positive 2Q charge down. So I'm going to draw a vector that is going down, and I'll label this the force of plus Q on the plus 2Q charge. So that's 1. Let's look over here. It's a negative and we got a positive, so this will be attracted up there. So I will draw another vector that points to that corner of the square. And we shall label this force of negative Q on the plus 2Q. And finally, we have this charge, which is also negative, so it will attract that plus 2Q charge that way. So force of negative 2Q on positive 2Q. From here on out, it's just simple vector addition. Eventually, once you get the x and y components of this and you add everything and you subtract it, you should get a resultant vector that points down that way, because you can tell that this distance is a little bit larger than here, so this is going to be quite weak. And since these two is plus 2 and plus 2, and then you have ones repelling down here, it's just going to be pointing down there. You just get a feel of it. And so you end up getting all the x and y components should sum up into here and here. And what you want to do is just find those magnitudes of those forces. So the total amount of forces going down will be the force right here, which is plus Q on 2Q. So that force, and then you need to subtract this by the y component of this force here, because as you can see, the y component of this diagonal force is going up and that's going down, so you must subtract those two. So we'll say the force of plus Q and 2Q minus the y component of the negative Q on plus 2Q, and I'll just write a little y there to signify the y component. Likewise, for this x component, we will add the x component of this force, because this force is going there, and so is the x component, so we will add those two. And so we look here, oh, it's the force of negative 2Q on plus 2Q, and then you add the x component of that diagonal force. And then we'll write a little x to make sure we know that that's the x component. So using this formula, electrostatic force equals K, Q1, Q2 over R squared. We're going to get the magnitudes of all of these different forces and add them and subtract them. So what I'm going to do is just make one really long, messy equation that calculates all this, a messy one doing all that, get two values, and then get the angle and the resultant one. So let's start with the y component. I'm just going to use this arrow, and I'm going to say that all this magnitude will be, and let's start calculating. So we'll start off with the plus Q on 2Q. So we do K, positive Q, little q, so that's going to be K 0.10 times 10 to the negative 6 coulombs, multiplied by 2Q, or just 2 times that. We do 2 times 0.10 times 10 to the negative 6 coulombs. And it's separated by 5 centimeters, or 0.05 meters squared. We'll take this and subtract it of the y component of this diagonal force. So we do minus K, and so we do negative, but since it's absolute value, it doesn't matter. It's basically the exact same thing. We just copy it. We'll do 0.10 times 10 to the negative 6 coulombs multiplied by 2q, because now we're doing these. 10 times 10 to the negative 6 coulombs. And as for the r, or the distance between them, since this is a square, if I draw a line here, we know that this angle right here is 45 degrees. And since all of these is 0.05, using special right triangles, we find out this side is x, this is x, and this side would be x root 2. So if you want to find out this distance, it's simply 0.05 multiplied by root 2. And so I will do that, 0.05 root 2, and then we'll square that. However, that only settles the r, but you need to do the x component of this, because what you just did here, this value, if you calculate it, it will just be the magnitude of this vector here, but you need to get that x component. Well, likewise, this would be x root 2, that's x, and that's x. So if I set this entire value equal to x root 2, because that's what that is, I set it equal to x root 2 real quick, and I'm looking for just x, because x is the x component. So all I have to do is divide this whole thing by root 2, and that will signify or represent the x component of this diagonal vector here. So all you gotta do is take this entire thing and say, oh, we'll divide it by root 2. And so you gotta stick this entire thing into your calculator, and you will get 0.0465 newtons. And so that solves the y component of all the forces. That's like the net force of the y component. So next you gotta find the net force in the x direction. And so we'll basically do the same thing. I'm gonna draw an arrow right here. All this equals to, you look at our first one here, negative 2q on positive 2q. So we're looking between these two. So we use this equation, k times 2 times, whatever they told q was, 0.10 times 10 to the negative 6, negative 2q, but same thing because absolute value. And take that all divided by the distance between them, which is 0.05, and you square that. And since this x component is in the same direction, we shall add it, plus the force of negative q on the positive 2q, but in the x component. So what you'll do is, since you basically did this exact same thing, you found that, okay, the y component is the x, but since it's a special 45-degree right triangle, the x component also happens to be just x. So you can just add all this. You don't have to think anymore. You just take this and shove it right here. So k 0.10 times 10 to the negative 6 coulombs, 2 times 0.10 times 10 to the negative 6 coulombs, all divided by 0.05 root 2 squared. And you take this whole thing divided by root 2. So stick this whole thing to the calculator, and you'll get 0.1695 newtons. All right, so this is F net, the net force in the x direction, and this is F net in the y. So let's redraw our vectors here. I'm gonna be lazy right here. The x component is that. Y component is 0.0465. Well, the resultant must be right here. We'll use Pythagorean theorem, C equals, and we'll square each of those, 0.0465 squared plus 0.1695 squared. That resultant force is going to be 0.175 newtons, or in the solutions in the workbook, rounded to 0.180 newtons. So that does it for the resultant force. All you need to do is find that angle theta. Well, to find that, you move this vector right here. It's the same thing. Oh God, it's not tip to tail. Well, pretend you never saw that. Imagine I drew it tip to tail because I'm an idiot. It's supposed to be right there. So you do opposite of adjacent tangent. You know how that works. 0.0465 over 0.1695. You did opposite, which is that, over adjacent, which is that. You move the tangent over, it becomes arctangent. Theta is 15.34 degrees. And so your final answer will be 0.180 newtons at 15.34 degrees below the horizontal. And that does it for part A. Alright, so part B wants you to find the net E field at this location if you remove the +2q charge. So what is the E field on that location? So let's recall the formula for the E field, which is E equals kq over r squared. And you'll find that it's extremely similar to the electrostatic formula, which is kq1, q2. All they did was take out 1q. So what does this mean? Well, let's remove this for starters because they don't want that. And let's just start drawing, the vectors for where the E field might be. So let's just start with this one. The E field will follow the path of a positive particle, your positive test charge. So we'll put a positive test charge here. And since it will repel downwards, that is the direction of your E field line. So you do, E field is kq of r squared, so that value would be kq of r squared, right? And we'll do the same here. We put a positive test charge right here, and you'll find that since it's negative, it's going to pull it to the right over there, or kq of r squared. Put a positive test charge here. Again, it's negative. It pulls it right up. Well, what do we have here? This diagram is exactly the same as this diagram, except you don't have +2q here. So that means when you do actually calculate these values here, you're just leaving out 2q, or you're leaving out this value here. So what you can do, since every single calculation above had it, all you need to do is take your final net answer for part A and divide it by that +2q value, because now you're taking it out. And it wasn't even in this equation to begin with. It's a shortcut, because since they don't want it, you just take 0.180 divided by that value, and you'll get your answer. So you do the E net is 0.180 newtons, but you divide it by that charge that they want you to take away, which is 2 times 0.10 times 10 to the -6 coulombs. And the units check out, newtons per coulomb. Well, let's punch it in real quick. I already did that, and you get 9 million, 900,000. And so you're right. 1, 2, 3, 4, 5 newtons per coulomb. But you'll see in your workbook that it says M newton per coulombs. M stands for mega, or times 10 to the -6. So you do 0.9 times 10 to, not -6, +6 newtons per coulomb, or 0.9 newtons per coulomb, which is how the workbook formats the answer, and that is part B. Okay, so part C wants to find out what is the E field right smack in the center right here of this square. So again, let's take our positive test charge and start drawing some E field vectors. So let's label these charges here. This is going to be number 1, this is 2, this is 3, and 4. So the E field right here on a positive test charge, because of particle 1, will be to the bottom right. It's going to repel the positive test charge here. But this negative charge is actually going to attract that positive test charge. So we can write the E field here is due to E1 plus E4. And you'll find the same story for 3 and 2. As a positive test charge in the middle, this +2q will repel it up here, and this -1 will pull it up. So we'll do E3 plus E2. And so let's take these two arrows, draw down here to analyze this a bit more. Okay. So it's a square, so that 45-degree angle gets corresponded up there. So that's still 45 degrees. this is all like still a special right triangle. So whatever values you get here, you know, those are x's, this x, your hypotenuse will always be x root 2. And so let's start looking at this. Because these two E field vectors have the exact same magnitude, you don't have to worry about the y component because there's an equal force pulling it here and here. And since they're both exactly the same, there's no y component, you just end up with a resultant, you know, x component. So when we do end up summing all this, we only need to worry about the x components. So now let's do, we'll do down here, E net is just E1 plus E2 plus E3 plus E4, but only the x component. Well, since if you add all these up, just those raw magnitudes, it's actually accounting for like, you know, the diagonal vectors, but you want to get the x component. So if you set those diagonal values equal to x root 2, like I said before, all you have to do is divide by root 2 to get x. So you have all those magnitudes, multiply it by root 2, and this represents the x component of all these E fields. And next, all you gotta do is just like plug stuff in. And so for both E1 and E2, as we said, E1 is between Q and plus 2Q, and E2 up here is between also plus 2 and Q. They're the same, so what we'll do is just multiply by 2. And we'll do just one of them, you'll see. So we do K, Q1, and since E is just KQ over R squared, we just do KQ. We'll do just the little q first, over R squared. And your R in this case, well, if this is 0.05 meters, and directly across here 0.05 times root 2, you take that, divide by 2 to get that, and you'll find that 0.05 root 2, but then you divide it by 2 once more, is 0.0354 meters. And that's going to be R in all these different cases here, 0.0354 meters squared. And all you have to do is take this, multiply by 2, since you have exactly the same one right there of the same magnitude, and then plus K, but this time we're doing the plus 2 Q's, these two. So we do K 2 times 0.10 times 10 to the negative 6 over R was 0.0354. And we'll take this times 2, and we'll take this entire thing times root 2. And once you multiply it all out, you'll get something like 3054701.295 newtons per coulomb. You simplify that to 3.1 mega newtons per coulomb, and mega for all the same reasons as just now. And to the right, because we ruled out the y components don't matter, it's just to the right. And that's part C.